Water, one of the most fundamental molecules as far as life is concerned. Life as we know it on this planet, and from our experience, cannot exist without the presence of water in its liquid form. This morning, we're going to be talking about water and what it is about the water molecule that makes it so important for life. So as we explore in this presentation the properties of water, what I want you to pay attention to is what is the underlying principle that accounts for all of these properties of water. If you don't pick up on it as we make our way through the presentation, by the time we're done, I will have mentioned it so many times that you will probably start to get tired of me saying the same thing over and over again. But it's really important that you understand the basis for why water has the properties that it has and what the implications of those properties are for the existence of life. So let's start talking about water, and we begin by looking at the structure of water, because from there we start to understand why water has the properties that it has, and then we can start discussing the implications of those properties for life as we know it here on the planet. And bear in mind, water is so central to everything that we know about life. It is so important for the existence of life as we know it here on our planet, that when NASA starts looking for even the possibility of life somewhere else, before they even look for the possibility of life, the first thing they look for is the presence of water currently, or the presence of water at some point in the past, indicating that there is at least a possibility of life existing now if water is present, or that life existed in the past if there is evidence of water existing in the past, particularly in its liquid form. So this is a clear indication of just how important water must be to the very existence of life. So it stands to reason that we should spend a whole chapter just investigating the water molecule and the properties of water. So let's get started. So, not surprisingly, when we look at the Earth and we recognize that about 70% of the Earth's surface is covered by water, there is this very real suggestion that water must be important in some form. And then when we start to look at the composition of life, and we've already talked a little bit about this, but as we start to think about the composition, the chemical composition of life, we start to understand that the vast majority of an organism is simply water molecules. You and I and most mammals are approximately 70% water. Other organisms are a little bit more. So in the case of watermelon, particularly the part that we eat, or lettuce, or something like that, the water content is up to 90% water and only 10% non-water molecules. Something like a jellyfish is about 80% water. But then there are other aspects of life where the water content is greatly reduced. So if you look at a typical seed that you might buy in a seed packet, the water content there is around 15% approximately. Very greatly reduced. But that also gives you an indication of the nature of the seed. Inside the seed, there is a little embryonic plant. And the fact that the water content has been reduced to such a low level explains why that little embryonic plant is in a state of stasis. Is it biochemically active? Yes, but the level of activity is extremely low, just enough to keep it alive. How do we reconstitute the activity of that little seedling? We actually soak the seed in water, a process called imbibition. And as the seed becomes rehydrated, the little seedling plant resumes its growth and very quickly emerges from the seed, utilizing the stored energy sources inside the seed, the proteins, the sugars, the fats, and other molecules that are stored in the seed to provide it with a food source. Eventually, as the seedling emerges from the ground and begins photosynthesis, it starts taking care of itself. But all of that begins by returning the water content of the seed and by extension the seedling back to around 70% that allows the chemical activity of the little seedling to resume again. So this is just, again, a further indication as to just how important water is. And when we start to look at that part of the earth that is occupied by life, again, we have to think in terms of the presence of liquid water. So when we think in terms of the oceans, no mystery there. I mean, the ocean is liquid water. But there are other environments that we could look at where we might go, but where is the liquid water? And the answer is, you just have to understand the conditions under which the water is present to understand why the water is liquid. So when you go to the deep ocean and you go to some areas, particularly in the middle of the Atlantic Ocean called the Mid-Atlantic Ridge, where lava is welling to the surface of the floor of the ocean because the two tectonic plates that carry North America and Europe are slowly separating from each other. There's a gap there, a split, that allows the molten rock to come to the surface, and it extends all the way down from north of Iceland through Iceland. Iceland actually sits right on the middle of this thing, all the way down through the middle of the Atlantic, and then around the end of Africa and up into the Indian Ocean. It is, in fact, the longest mountain range on the planet. It just happens to be covered by about 10,000 to 12,000 feet of water on average. But if you go into that area, you come across some regions that have big pipes coming up from the floor of the ocean, and hot water is coming out of that. But that hot water is around 600 to 700 degrees Celsius, and it's black in color because of all the dissolved minerals that it's picked up by percolating into the cracks in the floor of the ocean, coming in contact with the hot rock underneath, dissolving up minerals, and then emerging back out of some other cracks. And as it comes in contact with the cold water, because the water is at around 4 degrees Celsius, it cools relatively rapidly, and all the minerals start to come out of the water, hence the black color of the water. And they build large hollow pipes that the water comes out of, and these are called black smokers. And when you look around the edges of these black smoker pipes, you find ecosystems made up of crabs and fish and some tube worms that are called bloodworms. These are about 6 feet long, fully encased in tubes. And in the body of these bloodworms that are bright red because they contain hemoglobin, just like we do, there are little microorganisms. We call them archaea. They're close relatives of bacteria. They're prokaryotes themselves. We've learned about them previously. And they have the ability to process chemicals in the water as a source of energy. And they are the basis for these ecosystems. There's no use of sunlight at all. Photosynthesis can't exist. You're 10 to 12,000 feet below the surface of the ocean. No light can get there. Yet these ecosystems exist, and they are built around these microorganisms, these archaea, that process a chemical called hydrogen sulfide, H2S, sometimes called rotten egg gas. And they use that as a source of energy to convert carbon dioxide into organic molecules for their own use, but they in turn then get eaten by the worms or provide these organic molecules to the worms as in a relationship called a symbiosis. And then the worms are food for the fish and for the crabs and the other organisms that live in these ecosystems. And this is very, very unusual. And the water that is nearby these black smokers is at around 140 degrees Celsius. It's one of the hottest environments that we know life can exist in. And it's all because of these archaea. And of course, 140 degrees Celsius, you don't have to think very much to realize this is well above the boiling point of water. So why is the water liquid? Because of the sheer pressure of the ocean pressing down, it stops the water from boiling. And so you can get water temperatures that are well above boiling point and still keep the water at liquid, at a liquid state. And so life has figured out a way of making use of this environment. It's very bizarre, but it nonetheless succeeds because the water maintains its liquid characteristics. We could go into the deepest mine on the planet, which happens to be a gold mine in South Africa, just outside of Johannesburg. It is currently a little over 3.5 kilometers deep into the crust of the earth, but they're digging deeper because they know there are some very rich veins of gold about another kilometer further below, about 1,000 meters further below where they are. Their geological surveys have indicated that these veins of gold exist there. So they're digging deeper into the earth to get to these gold deposits. And if you go down into the mine to that very depth, I'm told it is very, very unfriendly to humans. The humidity is 100%. The temperature is well over 100 degrees Fahrenheit. It's very, very uncomfortable for humans. But biologists have been down there just to see if there's anything living down there. And you might think, you're that deep into the rocks, what could live down there? Well, not surprisingly, they're prokaryotes. They're actually bacteria. And what the biologists did was drill holes into virgin rock that had been exposed by the miners. In that rock, they found little pockets of water. In those pockets of water, they found bacteria living. They were processing minerals that had been dissolved out of the rock, and they were using that as a source of energy. There was not a lot available to them, so it's estimated that these bacteria divide about once every 1,000 years or so. So they're very, very slow growing, but they are very much alive. And the point here is they have not been near the surface of the earth for we don't know how long. We don't know how long they've been buried at these depths in the rock. And they are surviving quite well, thank you very much, in this very bizarre environment. I could take you to some caves in Mexico, where if you to walk in with anything less than a fully enclosed hazmat suit, you would probably die. The air is poisonous. The atmosphere is very acidic because of the gases that are present in the atmosphere and dissolved in water. They form a substance called sulfuric acid, which would eat the clothes off your back and then start eating your skin and the rest of your body. And yet, there are organisms that are living in here. And there are whole ecosystems in this environment. And they are built around, again, prokaryotes, in this case, again, archaea, that are able to process chemicals and extract energy and form the basis for the whole ecosystem living inside these very, very toxic caves. And in the case of the archaea, they form long, stringy material that hangs from the surface of the cave. And this is going to sound a little bit disgusting, but this is how biologists think. They look a little bit like a booger hanging out of someone's nose. And so they have been called snotites. These are the colonies formed by these prokaryotes hanging into the atmosphere so that they can harvest the gases and use them as a source of energy. And there are other organisms living in these environments as well, using the bacteria as the basis for the food chain and the energy source. What's the one common thread with all of these environments? That there's liquid water present. They may be really bizarre. It may be a stretch to understand why the water maintains its liquid nature. But the fact that it is liquid means that life has figured out a way to take advantage of it. And that seems to be the key. So long as there is the possibility for liquid water, doesn't matter what else is present, so long as there is the possibility for liquid water, organisms will figure out a way to take advantage of that environment. And typically, it's the prokaryotes that figure it out because they are so chemically flexible. It's one of the reasons why we recognize them as the single most successful group of organisms that have ever lived on the planet. And there have been time periods, particularly very early in the history of the planet, where things occurred that might have wiped life out on the surface of the planet. Yet because the prokaryotes, bacteria and archaea, were able to survive in some of these really bizarre environments and utilize them to their own advantage, they were able to hang on and hang around when any other types of organisms that might have been present were wiped out because of these changes, and were able to reestablish life again. And one of the ways that we now think about life on planets is that if the conditions on a planet, and by that we mean the conditions that we understand here on Earth primarily, start to occur that are considered to be favorable to life, life is almost inevitable. It is pretty much inevitable. And once life takes a foothold on a planet, it is very, very, very difficult to get rid of it again. You almost have to destroy the whole planet in order to get rid of life, because life will find a way to survive. That seems to be the situation. And we even know that there are some life forms here on our planet, and some of them are multicellular little animals that can even survive exposure to open space. They can survive being frozen and be resuscitated. They can survive being boiled and still survive. It is amazing what life forms can do in terms of survival. But in order to actually live and function, do more than just survive, they actually need the presence of liquid water. That seems to be the key. So I could go on and talk about all the bizarre ways in which life succeeds on our planet. But perhaps what we ought to do now, I think I've given you enough food for thought in terms of just how important water is, to think in terms of the structure of the water molecule and why that makes it so important. So let's move on and take a look at the structure of a water molecule. So building on what we've learnt in the last chapter about the structure of molecules and the fact that atoms come together to form molecules on the basis of wanting to either exchange electrons or share electrons to take on a noble gas conformation as far as their valence shells are concerned. We need to think about that in terms of the water molecule. So let me turn on the writing tool for the PowerPoint. And what we need to remember is that when we look at water with oxygen and hydrogen as the components, remember they're going to form covalent bonds, and those covalent bonds are going to involve the sharing of a pair of valence shell electrons, one electron from the oxygen, one from the hydrogen for each bond. But remember, the oxygen is way more electronegative than hydrogen, so consequently the electrons sit or spend more time at the oxygen end of the bond than they do at the hydrogen end of the bond. And so consequently there are these two partial negative charges at the oxygen end of the bond and a partial positive charge at the hydrogen end of each of the covalent bonds. And remember, these bonds are called polar covalent bonds as a consequence. These partial charges then mean that water molecules can hydrogen bond to each other. And the key here is that a single water molecule, because there are these four partial charges, can hydrogen bond to a total of 4 other water molecules. But it's more complicated than that, because each of these water molecules are in turn hydrogen bonded to another 3 water molecules, which are hydrogen bonded to another 3 water molecules, which are hydrogen bonded to another 3 water molecules, da, 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 da. You get the idea. If you have a container, a glass full of water, and that's the only thing that you've got in there, you've got trillions upon trillions upon trillions of hydrogen bonds, because all the water molecules that are in there, and there are literally trillions of water molecules in there, those water molecules are all hydrogen bonded to each other. And it's the presence of those hydrogen bonds and the polar nature of the water molecule that explain all of the key chemical properties that make water fundamentally important to life. That's it. So if you are puzzling over why it's water, if you're ever asked a question about why it's water, if you're ever asked a question about the chemical properties of water and you're struggling to think of an answer, just remember hydrogen bonds and polar covalent bonds, and you're probably going to be correct. There's very little about the chemical nature of water that cannot be explained in terms of either its polar nature because of the polar covalent bonds, or because as a polar molecule, it can form hydrogen bonds to other water molecule bonds, to other water molecules. So that's the answer to the most fundamental question we can ask about water. Why water? What makes it so important? That's it. And out of this stems everything else. So as we start working our way through the properties of water, just bear in mind that everything that we need to know about the properties of water begins with the fact that water is a polar molecule because the covalent bonds are themselves polar covalent bonds. And because of that, the water molecules can form hydrogen bonds, and that changes everything. So that's where we begin. So, first concept check for the morning. I know we haven't been going for very long, but we need to just throw this in here. First concept check. What is electronegativity and how does it affect the interactions between water molecules? You may puzzle over the what is electronegativity for a minute, but how it affects the interactions between water molecules, well, we've just been discussing that. But let's stop for a moment. We'll give you a chance to think that one through, and then I'll come back and explain the answer. Okay, so what is electronegativity? Reaching back to last week and back to chapter 2, you should, I hope, recall that electronegativity is the measure of the strength of the attraction between atoms and their electrons, and also atoms and electrons on other atoms. How strongly do atoms hold on to their own electrons? How strongly are they able to attract electrons in other atoms? So if an atom is strongly electronegativity, it not only holds on to its own electrons, but it has the capacity to at least pull very strongly on electrons in other atoms. And if it's strong enough, if the difference in electronegativity is great enough, it can even, the strongly electronegative atom can even pull electrons away from weakly electronegative atoms. That, of course, is the basis for ionic bonds. In this case, however, we're talking about covalent bonds. So yes, oxygen is more electronegative than hydrogen, but not electronegative enough to overcome hydrogen's own electronegativity and take the hydrogen's electron. So they have to share. But remember, sharing does not always mean equal sharing. Think about the candy bar example that I gave you in the previous presentation. So oxygen doesn't share the electrons equally with hydrogen, they share them unequally. That gives rise to the partial charges, which in turn give rise to the hydrogen bonds between the water molecules. And that means if you want to separate out water molecules from each other, and do that on a permanent basis, you have to provide enough energy to overcome all of those hydrogen bonds. And while a hydrogen bond may be the weakest form of chemical bond that we need to pay attention to, if you've got trillions and trillions and trillions of them, as you do in a simple container of water, then the amount of energy that you're going to have to provide is going to reflect not the weakness of a single hydrogen bond, but the sum total of the energy involved in all of those trillions of hydrogen bonds. And that can add up to a lot. So that changes everything that we have to in terms of how we start thinking about the water molecule. So let's move on and start talking about the important physical properties of water. So there are two related properties that emerge from the simple fact that water molecules are attracted to each other because they're polar. The first idea is called cohesion. And this simply means that the water molecules stick to each other because of those partial charges. Its cohesion is obviously the product of the formation of hydrogen bonds. And so when we start thinking about water molecules sticking to each other, we think about cohesion. The partner term that goes along with this is adhesion. Adhesion, again, talks about the stickiness of water molecules, but in this case, it's the stickiness of water molecules to any surface that has a charge on it. So not only will water molecules stick to each other, but they'll stick to anything that has a charge on it. So if a surface happens to have a charge on it, the water molecules will stick to it. And we can see the combined effect of cohesion and adhesion when we start thinking about some natural behaviors of water. So if you've ever tried to fill a glass with water, so let me draw a glass in. If you've tried to fill a glass with water, you know that not only can you fill it to the rim, but if you add carefully a few extra drops of water, you can actually get the water to sit above the surface of the glass. And the reason why this can occur is because of something called surface tension. This is the ability of water molecules to stick to each other more strongly than they stick to anything else. So the attraction between water molecules and air here is very weak, but the attraction between water molecules or between individual water molecules is significantly stronger. And that's what allows the water molecules to start rising above the surface of the edge of the glass. But more than that, with the force of gravity pulling on the water molecules, initially that pull is not strong enough to break the attraction between the water molecules, which further allows them to sit above the surface of the glass. Eventually, of course, you know that you add that one drop too many and the water spills over the edge. Then the weight of water, remember weight is the product of gravity pulling on something. The weight of the water, the force of gravity pulling on the water, now overcomes the surface tension and the water spills over. And there are some really good examples in nature of surface tension being put to use. So I'll jump over this picture and go to this one. So here's a spider walking on the surface of the water, and you can see that the weight of the spider is definitely pushing down on the water because you can see that the water is bowed where the legs of the spider are touching the surface of the water. So why doesn't the spider fall through? Because of surface tension. And there are two reasons why. Notice that it is not the point of the leg of the spider that's touching the water surface. It's a large part of the leg of each leg that's touching the water. And number two, there are lots of legs touching the water. So the weight of the spider is spread out over a large surface area. So very little of the weight of the spider is pushing down on any one part. And that's what allows it to overcome the surface tension. You can actually break the surface tension relatively easily by using soap. So if you really wanted to give this spider a bad day, if you added a drop of soap adjacent to where the spider is, that soap would break the surface tension and the spider would fall through and drown. But that's the reason why we use detergents and soaps to break surface tension. Now, the other feature that goes along with this is cohesion, the stickiness of water to, well, this is the stickiness of water to itself, that's surface tension. But adhesion, we can still see with the glass, because this time, let me put here, surface tension is cohesion. Here, if you fill the glass half full, you know that the water forms a surface. See if I can bring this back. Just hold on a second. Let's undo this. Oops. Let's see if we can end the show. It's not going to do what I want. No, it'll let me up. See if I can undo what I did here. Doesn't look like it. Yeah, okay. We'll keep going. Thought I kept the markings. Oh well. On the previous slides, you can see those. You can go back and see those. So let me just put the. Doesn't take very much to put this back in again. So that was surface tension. I've got to remember not to push the buttons on the pen. Okay, so we were talking about adhesion. So when you fill the glass with water, but you don't fill it full this time, you fill it half full. You know that the water forms a surface across the glass. But when you look at the edges, it's not flat. It actually comes up on the side like this. And that is called a meniscus. And it is the product of water being attracted to the glass itself. Glass has charges, the surface of glass has, I didn't spell that correctly. Should be a C in there, meniscus. So the water is actually attracted to the charges on the surface of the glass, and for a short distance, the attractive force between the charges on the water and the charges on the glass can overcome the force of gravity, and so the water literally climbs up the side of the glass. If the container is small enough, the meniscus actually forms a larger part of the surface area. The percentage of the surface area that is involved in the meniscus versus not in the meniscus is a function of how wide the container is. So if the container is narrow enough, the meniscus actually constitutes the full surface area of the water. And then we're talking about something called a capillary tube. So a capillary tube is simply a very, very narrow glass tube where the meniscus constitutes the total surface area in contact with the water, in contact with the glass tube. And if you dip a capillary tube into a solution of water, the water will instantaneously climb up the inside of the tube because of the attraction between the water and the glass surface of the capillary tube. It seems like magic. It looks like magic. But in fact, it's just a simple interaction between the charges on the water molecule and charges on the glass surface. And we do see these in play in the movement of water up a tree. So when water is lost from the leaves of a tree, water moves inside the leaf to replace the lost water. And as that water moves, because the water molecules are adhering to each other, cohering to each other, the cohesion, the movement of the water pulls on water molecules behind, which pulls on water molecules behind, which pulls on water molecules behind, which ultimately pulls on water molecules in the root. The movement of water into the root is a different mechanism, but once the water is in the root, it's all about the stickiness of water to itself that allows it to be pulled from the roots up the trunk, out along the branches, out along the twigs, into the leaves, and ultimately through evaporation, or what is rightly called transpiration, out of the leaves. And it's that simple loss of water out of the leaves, excuse me, and the resulting pulling force that's generated as the water moves into the leaves to replace that which is lost, that pulls the water up the trunk of the tree. Now, it also is aided by the fact that the little tubes called xylem tubes also have charges that attract the water molecules. So that aids in the movement because the water molecules themselves can climb up the inside of these tubes. And this is particularly important in your houseplants. If you fail to water them, you know that your plants start to wilt. But if you add water back in, the plants spring back up to life again because they need the water and the volume of the water to maintain the rigidity of the plant. And we'll talk more about that when we talk about plant cells in chapter 6. But one of the reasons why the water can move back up into your houseplants is not only because of the sticky nature of water to itself, the cohesive nature, but also the adhesive nature of water. These little tubes are so narrow that the water can climb up by capillary action. That's this idea that the water can climb up inside these very narrow tubes because of the attraction between the water and the surface of the tubes. We see that in the glass capillary tubes. We see that in these little tubes that form the xylem tissue, the water carrying tissue inside a plant. So water movement in a tree is no more technically difficult than understanding these two properties of water and what that allows water to do inside appropriately adapted tissue in a tree. The trees are simply taking, or life is simply taking advantage of these two properties of water to allow the water to move. We, on the other hand, we use very powerful pumps that can't do anywhere near as much work as a tree can do. Remember, the tallest trees on average on the planet are over 400 feet in height, and 400 feet is the height of a 40-story building, because a story is considered to be 10 feet. So this is a 40-story building. This is one of the large buildings downtown in Orlando, for instance. And it could be even more impressive than that because the root system might go down 100 feet into the soil. And so it's not just the height of the tree, it's also the depth that the roots are going into the soil. So 500 feet, let's say, maybe 600 feet, depending on how deep the roots go into the soil. And now we're talking a 50 to 60-story building. Now we're talking about something that is not that much shorter than the Empire State Building in reality, because it's about that's 101 stories. So we're talking, well, let's say half the height of the Empire State Building to be a little bit more conservative. And trees can move water up just by using the sticky nature of water, sticky to itself, sticky to surfaces. Quite amazing, really, when you think about it. When you think about the effort that we go to move water up vertical distances with our very powerful pumps, and we have to stage it in steps to be able to do it, whereas trees can move water these huge distances just by using the sticky nature of water. What can you really say? And it's quite amazing to think about it. And it's just the properties of water. So the next thing that we need to think about is the interaction of water with energy, because this also explains a lot about the reason why water is so important for life. One of the most impressive things about water is that water is liquid over the widest range of temperatures. for any substance that we know of. So you might ask, why is this so? And it comes down to that one thing that we talked about at the beginning, because of the hydrogen bonds. So in order to understand why it's due to the hydrogen bonds, we first need to think in terms of energy and what happens when you add energy to something. So when we start thinking in terms of energy, there are two sources of energy that are really important in biology: kinetic energy and potential energy. Potential energy is stored energy. Kinetic energy is energy that can do work, but it also happens to be the energy of motion. So when we talk about things being in motion, things moving, we say that they have kinetic energy. And when we take the temperature of something, what we're actually measuring is the average kinetic energy of the molecules that in the substance that we're taking the temperature of. And so when we add heat energy to something, what we're actually doing is increasing the kinetic energy of the molecules. The heat energy is actually a form of kinetic energy where molecules are concerned. And so when you add heat to something, you're increasing the kinetic energy of the molecules. And that's true with water. When you add heat to water, you're increasing the motion, the kinetic energy of the water. When you take the temperature of water, what you're actually measuring is the average kinetic energy of the molecules of water. So when you see an increase in temperature in a body of water, what you're actually seeing is an increase in the average motion of those molecules. So what does this have to do with hydrogen bonds? Well, remember, hydrogen bonds are simply electrical attractions between those weak positive and negative charges on the hydrogen and oxygen atoms of a water molecule. So as water molecules move around adjacent to each other, those electrical attractions are always forming and breaking. So long as the water molecules are in motion, they have the ability to break those hydrogen bonds. But as soon as they break them, new hydrogen bonds are going to form because the water molecules are always near each other. And the reason why water remains liquid over such a wide range of temperatures is simply that you have to put in such a large amount of heat energy to break all of those hydrogen bonds to be able to separate all the water molecules from each other so that the hydrogen bonds no longer become a factor in the behavior of the water molecules. And because you're dealing with trillions and trillions and trillions of hydrogen bonds, it takes a huge amount of energy, comparatively speaking, in order to be able to do that. And remember, when you add heat energy, when you increase the motion of the molecules, you're also increasing the temperature. So water remains liquid, fully liquid, from 4 degrees Celsius all the way through to 100 degrees Celsius. That's the widest range of temperature that any substance remains liquid of any substance that we know of. And that's one of the reasons why water is so unique. And that's why water lies at the heart of life as we know it. Because again, if it's dependent on the presence of liquid water, and water remains liquid over such a wide range of temperatures, and as we've seen, you can even manipulate the range that water is liquid by changing the physical conditions so that you can increase the range of temperatures at which water is liquid at. Remember the deep ocean? And we can do the same thing at the other end. We can keep water liquid below the freezing point by mixing chemicals in like salt and stuff. They lower the freezing point of water so that you can actually increase the liquid range for water. This is what makes water so amazing as far as it's present in its liquid form here on our planet and gives that wide range of environments that life can exist in. So the way we measure the effect on water in terms of adding heat energy and raising the temperature is to measure what is referred to as the specific heat. And we define the specific heat as the amount of heat energy that must be added to a gram of water to raise its temperature by 1 degree Celsius, or you could phrase it the other way as it's put here, or the amount of heat energy that needs to be lost from 1 gram of water to decrease its temperature by 1 degree Celsius. And that's always measured at 1 atmosphere of pressure and at a temperature of 15 degrees. That's where we do this measurement, at 15 degrees Celsius. And water has the highest specific heat of any substance that we know of. It takes more heat energy to raise the temperature of 1 gram of water by 1 degree Celsius than it takes to raise the temperature of any other substance. And again, you might ask why, and the answer is because of the hydrogen bonds. The fact that as you are raising the temperature, what you're trying to do is break all of those trillions upon trillions upon trillions of hydrogen bonds, and it takes a lot of energy to do that. And so even to just raise the temperature of a small amount of water by 1 degree Celsius involves a huge amount of energy. And this is so important that we actually define a unit of energy by the specific heat of water. And the unit of energy is 1 calorie. So when we start thinking in terms of energy and we start thinking in terms of calories, and notice I've written the calorie here with a small c because there is a big C calorie that has been used in the past as well, and I'll talk a little bit more about that in a minute. But the chemical calorie, the calorie with a little c, is defined as the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. And the yardstick that we use to measure that by is the specific heat of water, which defines 1 calorie. So 1 calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius. That's how important the water is. So when we start thinking in terms of the use of a calorie in our diet, we used to use the term calorie with a big C. So it was always written calorie. And the chemical calories were always written with the little c. And so this is the one that is identified by the definition. So what did the calorie with a big C stand for? Well, that actually stood for 1,000 calories. So if you go back historically and look at the nutritional labels on old food packets, you'll see that the nutritional energy was always given in calorie with a big C, but everyone understood that that was 1,000 chemical calories. But recently, it was decided to uniform or reach uniformity in the way we labeled everything. So the prefix for 1,000 is kilo. And so it was decided, rather than to use 2 different forms of the word calorie, identified by whether it had a big C or a little c, that we would use a common term, and we would use kilocalorie, the prefix kilo, to identify 1,000 calories. So now when you look at the nutritional label on food, it's given in kcals, which is a kilocalorie or 1,000 calories. So when we talk about 2,000 kcals, that's actually equivalent to 2 million calories. And if you feel so inclined, you can actually figure out how much energy that's actually equivalent to in terms of volumes of water. And I did this once just out of curiosity. And it's equivalent to enough energy to raise the temperature of about 2.5 tons of water, about the weight of a small car, by 1 degree Celsius. It's an enormous amount of energy when you think about it. And that's the amount of energy that you need to take in on an average day just to keep yourself alive and do an average set of activities. These are not arbitrary numbers. These are things that actually become quite important when we start thinking in terms of our health. And those of you who are going into the health industry or health sciences in some form or another, are almost certainly going to come across this as part of your career, and that's most of you. So these are some ideas that you probably ought to pay attention to because these can become beneficial. The other unit of energy that you'll encounter, and particularly in the health sciences, is going to be the joule and the kilojoule. And the reason why is because this is the metric measure of energy, and most of the units that we use in the health sciences are based on the metric measures, what is called System International, or SI system. And that's built around the kilo for mass, or kilogram for mass, the meter for length, the liter for volume, and then seconds and minutes for time. And all the other units are derived from those basic units. And the kilojoule, or the joule, is the unit of energy. And you will likely come across that more frequently in your health science work, simply because of the use of that system in the health sciences. So now we have another important feature of water, the fact that water can absorb huge amounts of energy and not increase in temperature very much. Because if it requires a lot of energy to raise the temperature of water by a small amount, that means large bodies of water can absorb huge amounts of energy and not really change temperature very much. And we see that effect anywhere where you are close to the ocean. So I used to live here in Southern California, in this region of Southern California. In fact, I used to live out here in the San Bernardino area. And I can tell you that this temperature range is very, very accurate. It could be 100 degrees out in San Bernardino. And by the way, we're only out in San Bernardino. We're only about 80 miles, maybe 90 miles from Los Angeles. So the distance is not very far. And yet the temperature range is quite significant. Down on the coast, all along the coast, the temperatures are very mild. But the reason is very obvious, because the ocean is itself quite cool compared to the land inland. Now, what you have to bear in mind is that these temperatures are not temperatures of the surface. These are temperatures of the air above the surface. When we talk about the daily temperatures, we're not measuring the surface temperature, we're measuring the temperature of the air above the surface. If you take a look at the meteorological boxes that they keep all the equipment in, where they take the temperatures, there's housed about 6 feet above ground level, because we don't live on the land. The vast majority of our body is in the air above the land. So that's what we really worry about. What is the temperature of the air, not the temperature of the ground? And what's important here is that land always absorbs heat energy, but then radiates it back into the air and heats the air up above the surface of the land. And if you don't believe me, take a walk out into a parking lot and feel how hot the air is above the surface of the parking lot. Then step onto the sidewalk and then step onto the grass. And notice how different the temperature of the air is above all three. Because the land radiates heat energy back into the air. Bare ground radiates it, or a black parking lot radiates the heat energy back into the air much better than concrete, much better than sand, much better than grass, in that order. And so as you cross from the black parking lot to the concrete sidewalk to bare ground to grassy areas, you'll notice the change in temperature, quite significant change in temperature. And then if you go close to a lake, you'll notice that the temperature is even cooler there. Because again, the air above the water is much cooler because the water itself is much cooler than the surrounding land. Because the water is absorbing all of that heat energy, but not reflecting it or radiating it back into the air again and heating the air up. The reverse is true in winter. Because the air above the ground is now going to be cooler and the ground doesn't have a lot of heat energy to radiate up into the air is going to stay cool. But the air over the ocean is going to be a little bit warmer because of all that heat energy in the water. It now starts to warm the air up above it because it's got heat energy to give to the air. And so the ocean will remain relatively constant in temperature between summer and winter. Will it go up and down a little bit? Oh, sure. And we notice that here in Florida. The ocean temperature off the coast of Florida goes up and down between summer and winter. And we pay attention to that because in summer, as the water heats up, that becomes fuel for a hurricane that comes by. The hotter the water temperature, the more intense the hurricane is going to be, and the more likely the hurricane will develop along the way. But here in Florida, we're no more than about 60 to 70 miles from the coast, but we still notice these temperatures, even though we've got water on three sides of the peninsula. We still notice these temperature effects between summer and winter because we do see the heating effect. And that's the reason why in summer we get the thunderstorms coming in with the sea breeze, because the air that comes in, blowing in from over the ocean, is cooler than the hot air sitting over the land, and that cool air stays lower down and pushes the hot air up into the atmosphere, and that's what triggers the thunderstorms, the movement of the air into the atmosphere. So we can explain a lot of what we see, a lot of our climate and a lot of our weather by understanding the nature of water and its effect on the air and its ability, the ability of the ocean to absorb heat energy. And we used, excuse me, we used to think at one point that even the ocean could act as a reservoir of all the extra heat energy that's being absorbed because of global warming. Because there was a time, a period of around 10 to 12 years, where even though we knew that heat energy was being trapped, we couldn't see any large change in overall global temperatures. And we thought, well, the ocean is helping us out here. But as people have continued to measure the temperature of the ocean, we now know that it was a false sense of security, because all of that heat energy we're now starting to realize has changed the heat profile of the ocean. And we find that the ocean itself, the heat profile of the ocean has changed. We're finding that deeper areas of the ocean are now measurably warmer than they have been in the past. All of that heat energy that we thought the oceans were buffering by absorbing it and keeping the global temperatures a little bit cooler, all that was doing was being stored deeper and deeper in the ocean. And now that's coming back, because now we're finding that we've run out of that storage capacity of heat energy in the ocean, and the global temperatures are starting to rise again. But we've now got a warmer ocean than we should have. And that can have consequences. There are some really serious potential consequences if the ocean temperatures continue to rise. We don't have time to talk about it very much right now, but maybe we can talk about it at another point in time if we get a chance. But this is, again, another effect of the ability of water to absorb huge amounts of heat energy and not raise temperature very much, because you're dealing with all of those hydrogen bonds, and you can't argue but that there must be huge numbers of hydrogen bonds between all of the water molecules in the ocean. And that means that it's going to take a huge amount of heat energy to get the ocean temperatures to rise. But now we're starting to see that happening, which tells us that a huge amount of heat energy is being trapped in the ocean. Then not only do you need to put in a huge amount of energy to get the water to rise in temperature, once you get it to the point where it's boiling at 100 degrees Celsius, you need to add in extra energy again to get it to change from liquid to gas state, what is referred to as the heat of vaporization, or the latent heat of vaporization. And as you might expect, again, water has the highest latent heat of vaporization of any substance that we know of. And again, you might expect that this is due to the presence of those hydrogen bonds, because again, you've still got to break all of the hydrogen bonds to get the water to go from liquid to gas state, because in gas state, excuse me, the water molecules are moving fast enough that they can literally break all the hydrogen bonds and move away from each other and become independent water molecules without having to consider the hydrogen bonds, because they no longer matter. They just don't form up anymore. The water molecules get far enough apart from each other. So you have this added amount of energy, the latent heat of vaporization, that you have to add in to convert it from boiling liquid to gaseous water. And so this is, again, the reason why it takes so much energy to get water, not only to get to the point of boiling, but at the point of boiling to change from liquid to gas, to turn to steam. The converse of that, or the reverse of that, is that when water condenses from steam to liquid water, all of that heat energy has to be given off. So we can use these two observations, or we need to be aware of these two observations because they have consequences. We can use the evaporation of water for cooling, and we do. We cool our bodies down by sweating. Sweat is just water that is secreted by the sweat glands. It evaporates off the surface of our skin, and of course, as it goes from liquid to gas, it's got to be taking up heat energy from somewhere. That heat energy comes directly out of our skin. It's a way of getting the excess heat out of our body. We can use it as cooling. However, it is dependent on the ability of the water to evaporate. So if the humidity of the air, the water content of the air, is very high, then the ability of sweating to cool us down becomes greatly reduced, because the humidity, the relative humidity, how much water there is in the air, determines how well the water can evaporate. And here in Florida, that becomes a problem in summer when the humidity is very high. We find that it is very difficult to cool yourself down by sweating. And in fact, the consequence of that is heat frustration and heat stroke. It's very, very easy to become overheated in Florida in summer if the humidity is high. And you need to be very, very aware of that, because sometimes you may not be aware of the fact that you're not really cooling yourself down very well, because while you may be sweating and you're soaked in sweat, it's not evaporating and carrying the heat away. You're just losing water. You're becoming dehydrated, which is adding to the issue. And when you start to get heat prostrated, you, again, may not be aware of it, but others can tell, because your skin becomes blotchy. You start to get white blotches all over your skin as you become heat prostrated. That's the point to get into the shade, get water into, and cool down, because the next is heat stroke, and that becomes a medical emergency. And again, those of you who are heading into the health sciences in some form, you're going to learn more about this, because this becomes a real issue for people, and it is very much an issue here in Florida and across the South, and anywhere where evaporation becomes an issue. In the Southwest, so in Texas or Western Texas, Arizona, New Mexico, California, where it's a dry heat. There's not a lot of humidity, but it gets hot. Evaporation works really well. And in those locations, early forms of air conditioning, and in some cases it's still used, simply involved spraying a mist of water into the air and allowing that to evaporate and cool the air down. And that was the way you cooled the air down for air conditioning purposes, known as swamp cooling. And you've seen it at NFL games and places like that, where the players have benches where they're spraying a mist of water. That the evaporation of that misting water cools the air down and provides them with a cooler environment to sit in so they can keep themselves cool. It's just taking advantage of water's ability to absorb a lot of heat energy as it converts from liquid to gas. Oh, I said the converse. I mentioned that there is a converse to that, but I hadn't talked about it. So when steam condenses to liquid water, a lot of heat energy has got to be given off as well. All that latent heat of vaporization has to be given off. And as the water cools down from boiling temperature down, again, heat energy has got to be given off. And this is the reason why steam burns are some of the most painful and most serious burns of all, because of the sheer amount of heat energy that's being given off as the water condenses from gas to liquid. You've got to be aware of this. That's the reason why you should not expose yourself to steam. If you're going to open something where a lot of steam is going to be released, protect yourself, because your skin can get burnt very, very easily, and it's very, very painful, because the amount of heat energy penetrates deep into the skin and not only affects the surface of the skin, but goes deep and affects the underlying layers of the skin as well. And it can be very painful and take a lot of time to heal from. Steam burns have to be taken very, very seriously. Then one of the more odd features of water is that the solid floats on the liquid. Now, we don't necessarily view that as being odd, because we're used to seeing ice floating in water. It's how we cool our drinks down. We put ice cubes in the drinks, the ice floats, and over time it cools the drink down. But here's the thing. If ice behaved like a normal solid, it shouldn't float. It should sink straight to the bottom of the glass. The fact that it floats is the odd behavior. As much as we're used to that, that really is odd. It's totally out of line with what a solid ought to do. So why does ice float in liquid water? Well, the answer is what is seen in what happens as water cools down and the water molecules start to slow down. Because remember, whatever water is liquid, the water molecules are able to move. But as you start to cool the water down, as you take the heat energy out, as you lower the kinetic energy of the water molecules and they start to slow down, we have to start thinking about what happens to the hydrogen bonds. And what we realize is that those hydrogen bonds start to become more serious, and they become more relevant in our thinking about the water molecules, even more relevant than they were before. Let me go to the diagram, because that helps explain what's going on. So as the water continues to cool down, the water molecules slow down, but at the same time, the water molecules can also get closer and closer together. And this is what normally happens when you cool something down. The molecules get closer together. Things shrink as things get cooler. Things move closer together in terms of molecules. So the water molecules are getting closer and closer together. At the same time, the water molecules are slowing down, and it's harder for them to break the hydrogen bonds. At 4 degrees Celsius, the water molecules are as close as they're ever going to get to each other, and the hydrogen bonds start to take on a more serious form. As the temperature moves below 4 degrees, the water molecules themselves start to slow down, and some of the hydrogen bonds start to become permanent. And they start to lock the water molecules in place. And as we cool it even further, more and more hydrogen bonds become permanent links between the water molecules. And the water molecules get locked into a rigid structure called a crystalline structure, and ice crystals start to form. But it's the nature of these hydrogen bonds in the ice crystal that are the key, because the hydrogen bonds, like all chemical bonds, have a feature called the bond length. It's the distance between the molecules in the bond type, and in this case, in the hydrogen bond. And it turns out that the bond length of a hydrogen bond forces the water molecules further apart in ice than they are at 4 degrees Celsius. So at 4 degrees Celsius, the water molecules are really close together, as close as they can ever get. Once you start to cool below 4 degrees Celsius and ice starts to form up, the water molecules move apart from each other again and get locked into the rigid ice crystal structure. And as a consequence, ice becomes less dense, because density is measured as the number of molecules per unit of volume. So if you have the same volume of ice as you have of water at 4 degrees Celsius, there are going to be more water molecules in that volume of water at 4 degrees Celsius than there will be in the same volume of ice. And because there are fewer water molecules in the volume of ice, the ice is said to be less dense than the water. And something that is less dense will float in something that is more dense. So ice floats in water. And there's approximately 10% fewer water molecules in a volume of ice than there is in the same volume of water at 4 degrees Celsius. So consequently, about 10% of ice sticks above the surface of the water, and the remaining 90% is below the surface of the water. And so when someone says to you, you know, the amazing thing about an iceberg is that 90% of it is below the water, actually, they've got it wrong. The amazing thing about an iceberg is that 10% of it is above the surface of the water. Because remember, if the iceberg behaved like a standard solid, none of it should be present, it should be visible above the surface of the water. It should be sitting on the bottom. Now, the added advantage of ice floating, and this is the advantage for organisms that live in lakes that get frozen over, or live in the Arctic and the Antarctic, where ice covers the surface of the ocean, is that the ice itself now acts as an insulator, protecting the liquid water underneath from the freezing air above. And so once you get a thick enough layer of ice forming, the remaining water underneath remains liquid. Now, granted, it's at 4 degrees Celsius, not something that we would want to swim in, but the organisms that live there have adaptations that allow them to survive in those environments. And it's this simple observation, the fact that that life exists quite well in environments where you have ice covering liquid water, that has got NASA excited about going to a moon of Jupiter and a moon of Saturn, because each of those have a thick icy layer, in some cases up to 2 kilometers thick, so it's not going to be easy to get through, with an underlying liquid ocean, because where the ice cracks, we can see evidence of water coming up to seal those cracks again. So we know there has to be liquid water underneath. And given that life can exist under ice, there's the possibility that maybe life has formed in the liquid water underneath these layers of ice. And we know that life can exist in environments where there's no photosynthesis. Think about those black smoker environments again. Life can utilize chemical energy rather than light energy to form organic molecules. So it's possible that there are life forms living in these oceans on these moons, and NASA is planning to go and take a look. They're going to send autonomous submarines up, and they're going to melt a hole through the ice, take a bit of time, but it can be done, of course, and drop the submarine in, and it's going to go around and search around and report back on what it finds. And while I don't believe the life forms, if they exist, are going to be more complicated than probably bacterial-like or small unicellular eukaryote type organisms. I don't think it's likely to be more complicated than that. I think it would be kind of cool if the last image one of these little submarines sent back via its television camera was a big old set of jaws with them very large looking teeth. Because I think that would get everyone's attention if that was what we saw. I don't know whether that's the case. I doubt it, if that's what we're going to see. But I think there's a very real possibility that life might have evolved. Life may have come into existence on those moons, because the environment certainly matches the sorts of environments that exist here on the planet. We know life exists there. So that's the possibility, and NASA's going to go take a look. Then the final property of life that we need to talk about is the fact that water can function as a really good solvent. And this comes down to its polar nature. Again, it's got charges, these partial positives and partial negatives, as a consequence of the polar covalent bonds between the oxygen and the hydrogen in the water molecule. So that means that anything that is charged itself, that has either positive or negative charges on it, will easily dissolve in water. And as a consequence, we describe those as being hydrophilic or water loving. So hydro for water, and philos is one of the three Greek words for love. So hydrophilic means water loving. And then anything that is uncharged or non-polar, so non-ionic or non-polar, is said to be hydrophobic. It won't dissolve in water and won't interact with water. So again, hydro means water, and phobia means fear. So these are water-fearing substances. They don't dissolve in water. And you can think of some really good examples of this. So a good hydrophilic substance would be salt or sugar or something like that. Got charges on it that the water molecules will interact with. Something that is water-fearing or hydrophobic could be a wax or an oil, something like that. They're all non-polar. And as we look at the important molecules of life, when we get to chapter 5, we'll be actually looking at their chemical properties in terms of, are they water soluble or not, and why. And we'll see some really good reasons why, starting with the next chapter, chapter 4, when we talk about the 30% of organisms that is not water, that is built on carbon. More to come in the next presentation. So we've talked about the fact that salts are really soluble in water. Table salt, sodium chloride, dissolves simply because each sodium ion in a salt crystal gets surrounded by water molecules. And that layer of water molecules is called a sphere of hydration. So if something dissolves in water, it does so because a sphere of hydration can form around it. And so spheres of hydration form around the individual sodium ions and the individual chloride ions. And that sphere of hydration breaks the ionic bond between them. And so they go into solution because they are no longer attracted to each other. If you allow a salt solution then to evaporate, let the water evaporate, you can get the salt back again, because as the water evaporates, the ions start to see each other again, and the ionic bonds form up again, and the ions form the salt crystals and crystallize out as the water evaporates. So again, the ability of water to dissolve things is really important, because not only does water need to function as a solvent, but it turns out that all the cellular chemistry that takes place inside cells takes place in water. So if a chemical is going to take part in cellular chemistry, it first needs to be soluble in water. And that poses a problem for some of the large biological molecules, as you'll see when we get into chapter 5, because they are largely built from carbon and hydrogen. And carbon forms non-polar covalent bonds with itself and also forms non-polar covalent bonds with hydrogen. And so as a consequence, we might expect hydrocarbons, molecules composed of hydrogen and carbon, to be very non-polar and therefore not soluble in water. But it turns out that chemical groups that are attached to this carbon chain change the chemical properties of these very large molecules and make them very soluble in water, because the water is attracted to these chemical groups because they are themselves polar and allow the water molecules to form a sphere of hydration around the very large biological molecules, and they can therefore dissolve in water. We'll see this will be part of what we talk about in chapter 4, because we'll talk about the chemical groups, and what we talk about in chapter 5, because we'll then be looking at the large biological molecules and look at what chemical groups change the chemical properties and make them soluble, or keep them non-soluble or insoluble, as the case may be. So one of the important ideas that we now have to address when we think in terms of solutions is how to represent a solution biologically and chemically. And the answer that has been created by chemists is what is known as a 1 molar solution. So the standard measure of concentration is a 1 molar solution. And you can, the definition of a molar solution is one mole of solute, and the solute, of course, is the stuff being dissolved, in 1 litre of solvent, which in the case of biological molecules or biological solutions is water and there's a very important caveat here, final volume. So the next thing is to be able to figure out what a mole is. Let me move the text out of the way here a little bit, put it over to the side. Actually, I'll put it up. I'm going to move it up so that it's right out of the way from where I'm writing. So the definition of a molar solution is 1 mole of solute in 1 litre of solvent, final volume. 1 mole so 1 mole is the gram equivalent of the molecular weight, and I'm going to abbreviate this, molecular weight of a substance Apparently I can't write down here. Too far. Yeah, let me continue up here of a substance. And it contains Avogadro's number of molecules. And Avogadro's number is an inordinately large number. It's 6.023 by 10 to the power 23. Actually, let me erase that and do it a little bit neater, I think, because this is a number that you will see a little bit. 6.023 by 10 to the power 23. So that's Avogadro's number. It's a large number, but the beauty of Avogadro's number and its relationship with a mole is that if you have a mole of something, you know exactly how many molecules of it you have. Because by definition, if you have a mole of something, you have 6.023 by 10 to the 23 molecules of that substance. So, trying to remember what the next slide is because I can't remember. Yeah, it's a break slide because we want to do I want to show you how to do a calculation. So let's go to the break slide because it'll be a good way to show you how to do a calculation for molar substances. And I've got some worksheets for each of the chapters, and the worksheet actually guides you through how to do a molar calculation. So I'll make sure that I send out those worksheets for you. I'll make sure that those get sent out so you can start working on those and see how to do molar calculations. But I'll work a molar calculation for you here. So let's go to the break slide and take a look at this. So 2 questions in this break slide. The first is explain the saying, it's not the heat, it's the humidity. And then the second is how many grams of glucose, molecular weight 180 daltons, are needed to make 500 mils of a 1 molar solution. So there's our molar calculation. So let's take a look at the it's not the heat, it's the humidity saying. Remember we were talking about being able to evaporate water for cooling the body down, and that it's a function of the humidity here in Florida because our humidity is really high. It means that the evaporative cooling of our body doesn't work very well because the more water is already in the air, the less evaporation can take place from our skin. Whereas if you've got a dry heat, very low humidity, doesn't matter how hot it gets, the water can evaporate and keep you cool. So long as the water can evaporate, you can keep cool. And so long as you keep replacing the water that's being lost, you'll stay cool. It's when you either can't lose the heat because the evaporation is not taking place rapidly enough, or the evaporation takes place so rapidly that and you don't replace the water that you become dehydrated. Either of those are bad news. So you really do need to pay attention, and particularly here in Florida in terms of loss of evaporation because of the high humidity. It becomes really easy to become overheated. So that's a relatively easy one to explain. The calculation in terms of molar mass and molar calculations, that's a little bit more difficult. So this will take a little bit of time, but follow through with me and I'll show you how to do this. So the first thing in order to do molar calculations is to have the chemical formula of the substance. So glucose has the chemical formula C6H12O6. So there are 6 carbons, 12 hydrogens, and 6 oxygens. So carbon has the mass of 12 Daltons. Hydrogen has a mass of 1 Dalton. Remember, all of this you can get from a periodic table. Oxygen has a mass of 16 Daltons. If you're working with chemicals in a chemistry lab, you'd look on the side of the bottle, it would give you the molecular weight. It would be present on the bottle. So if we think in terms of the mass of carbon, well, we've got 6 carbons, so that's 6 times 12, which gives us a mass of 72. Hydrogen, we've got 12 of those, so it's 12 times 1, which is 12. And oxygen is 16, and we've got 6 of those, and that's 96. When you do the math, that adds up to 180. So that's the molecular weight for glucose. So that's why that's given as the molecular weight in the equation. Now, to make up a molar solution, remember, a molar solution is 1 mole of substance in 1 liter of solute. So 1 mole of glucose equals 180 grams. So this is why the definition says the gram equivalent of the molecular weight. The molecular weight is 180, so the gram equivalent is 180 grams. In other words, molecular weight in grams. So to make a molar solution, so a 1 mole of glucose is 180 grams in 1 liter, and its final volume. Now, what does that mean, 1 liter final volume? It means that if you take a liter of water and add the 180 grams of glucose, it will dissolve, but your final volume is not going to be a liter, because that glucose is going to take up some of the space and the volume is going to increase. You know this if you've ever tried to make lemonade. You take a little bit of water, you add a lot of sugar, the volume goes up because of all of that dissolved sugar. So to make a 1 liter solution final volume, you start with less than a liter of water, add your 180 grams of sugar to that, because it's very soluble, it'll go into solution. And then once you've got the sugar in solution, you add extra water to bring the volume up to 1 liter final volume. Then you've got a 1 molar solution. And so that's what you would do to make a 1 molar solution. So once you know how to make a 1 molar solution, everything else is just about ratios. So we're asked to make a 1/2 liter of 1 molar solution. Well, if a 1 molar solution is 1 mole in 1 liter, it stands to reason if we want only 1/2 liter of that, all we've got to do is divide by 2, because 500 mils is 1/2 liter. So if we want 1 mole in 1 liter to make a 1 molar solution, 1/2 mole in 1/2 liter is the same thing. It's the same ratio. 1/2 mole in 1/2 liter is the same ratio with 1 mole in 1 liter. So to make 500 mils of 1 molar requires not 180 grams, but 90 grams in 500 mils final volume. So this is how we do molar calculations. How important is this? For most of you that are going on into the health sciences, not that much, unless you're planning to go to medical school or dental school, vet school or something like that, in which case you're going on to do more biology, you're also going on to do chemistry classes, and these calculations will be part of those classes. As far as going into the allied health sciences and the nursing program, these are probably not going to be that important as far as the calculations are concerned. But being able to understand what a molar concentration is, that becomes really important for what we're going to talk about next. So let's move on and talk about the next part of the puzzle. How can we use our understanding of molar concentrations to understand a very, very important feature of water-based solutions, like a cell, like our blood, like anything that uses water as a solvent. So let me move this back down to the bottom again, so it's not quite so distracting. So one of the things that we now recognize about water is that if you have a container of absolutely pure water, the purest water that you can get hold of, which in a science lab would be something like triple distilled water, where you take the original water that's been already filtered to get most of the contaminants out, you boil it, capture the steam, condense that back to water again, take that water, boil it a second time, capture the steam, condense that out, take that resulting water, boil it a third time, capture the steam, and condense it back to the water, so that you've basically removed every possible contaminant that's in there, and all you've got left is pure water. You actually don't have a solution of just water molecules, because it turns out that water molecules undergo a process called dissociation, where the water molecules break down into two very distinct ions. So a single water molecule, a single water molecule actually breaks down, and we can draw this with a bidirectional arrow because it is reversible, to a hydrogen ion and a hydroxide ion. But because there are negative charges on the oxygen of water molecules, this hydrogen ion does not remain free as a hydrogen ion in the solution. It actually gets attracted to a water molecule. And so that gives rise to what is called H3O+, or the hydronium ion. So in fact, the dissociation doesn't involve a single water molecule, it involves two water molecules. One of them breaks down to give the hydrogen ion plus the hydroxide ion. The hydrogen ion then goes ahead and becomes associated with the second water molecule to give this H3O+ ion, which is called the hydronium ion. Now, it's not a lot of water molecules that break down. It's a very, very low number, 1 in 554 million. But when you think in terms of the total number of water molecules present in, say, a mole of water molecules, right? We just talked about moles on the previous couple of slides. A mole, remember, contains 6.023 by 10 to the 23 water molecules. That's a huge number compared to 554 million. So even if it's only 1 in 554 million water molecules in a mole of water that are breaking down, given the huge size of a mole of water molecules. We're still talking about a lot of water molecules dissociating. And by the way, 1 mole of water, that's 18 mils of water, and it occupies 1 cubic centimeter. Those are definitions that are built around volumes of water. So in your average bottle of water, which contains 500 mils, there are many hundreds of moles of water molecules, meaning a lot of water molecules in those bottles are undergoing this dissociation. That means in a volume of water, we can actually measure the concentration of hydrogen ions and hydroxide ions in that pure water. We do those measurements at 25 degrees Celsius. So when we have a pure volume of water and we measure the concentration of those water molecules at the ions that are the breakdown product of the water molecules at equilibrium. So let me put in here at equilibrium, because this is important. It's got to be at equilibrium. The concentration of hydroxide ions and hydrogen ions is both equal to 10 to the minus 7 molar. Why equal? Because 1 water molecule gives 1 hydrogen ion and 1 hydroxide ion. So each time a water molecule dissociates, breaks down, you get 1 hydrogen ion and 1 hydroxide ion. So at equilibrium, when the water molecules are dissociating, the number of hydrogen ions and the number of hydroxide ions must be exactly the same. And the measured concentration is 10 to the minus 7 molar. Very small concentration, but nonetheless, very measurable. Now, I want to introduce you to another shorthand because I'm going to start using it. In fact, I'm already using it on this slide. So let me move the text out of the way for a minute. Put it up here so you can see the equation at the bottom. So the shorthand is that anything in square brackets is concentration. So down here in my equation where I've got hydrogen ions in square brackets and hydroxide ions in square brackets, what I'm talking about here is the concentration of hydrogen ions and the concentration of hydroxide ions. So anytime you see me put something in square brackets, that's the chemical shorthand for saying the concentration of whatever's in the square brackets. So what are we talking about here? Well, it turns out that when you dissolve ionic substances in water, they break down into ions. We know that. And as a consequence, when we look at the breakdown of ionic substances when they're dissolved in water, and that breakdown is at equilibrium, we can define what is called the dissociation constant. So the dissociation constant is determined when the dissociation, the breakdown, is at equilibrium. So for water, that is at 25 degrees Celsius when everything is at equilibrium, when the hydrogen ion concentration and the hydroxide ion concentration are both equal to 10 to the minus 7. And we calculate the dissociation constant by multiplying together the concentration of hydrogen ions and the concentration of hydroxide ions. So that becomes 10 to the minus 7 multiplied by 10 to the minus 7. And when you multiply powers of 10 together, you add together the exponents. So that's minus 7 plus minus 7, which equals minus 14. So 10 to the minus 7 multiplied by 10 to the minus 14 minus 7 is a value of 10 to the minus 14. And that is the dissociation constant of water. Why that's important is because that product, that value of 10 to the minus 7, the product of multiplying the hydrogen ion concentration and the hydroxide ion concentration together does not change. So what is important about that? It means that if one of the two ion concentrations, the hydrogen ion concentration or the hydroxide ion concentration, changes, the other one must change as well, but in the opposite direction. So if the hydrogen ion concentration goes up, the hydroxide ion concentration must go down so that the product still equals 10 to the minus 14. Likewise, if the hydrogen ion concentration goes down, and the hydroxide ion concentration must therefore go up so that the product, the dissociation constant, the product of the hydrogen ion concentration and the hydroxide ion concentration still equals 10 to the minus 14. And that establishes the basis for the pH scale, a way of measuring hydrogen ion concentration. So here's what we know. If we have hydrogen ion concentration and hydroxide ion concentration, we know that for pure water, both are 10 to the minus 7. And therefore, the product, multiplying the two together, equals 10 to the minus 14. So, how low can the hydrogen ion concentration, how high can the hydrogen ion concentration get and still provide us with a product of 10 to the minus 14 if the hydroxide ion concentration goes down by the same amount? Well, 10 to the 0 is the highest level of hydrogen ion concentration, because going in this direction is an increase in hydrogen ion concentration. And so that means the lowest hydroxide ion concentration must be 10 to the minus 14. Likewise, going in this direction, it's a decrease in hydrogen ion concentration. And so it can get down to 10 to the minus 14, and that means this is 10 to the 0. But the only ion concentration that we're really interested in is the hydrogen ion concentration. We're not interested in the hydroxide ion concentration. Why? Because it turns out that the concentration of hydrogen ions has a very significant effect on chemistry, and particular cellular chemistry. So it's important to have a way of being able to measure hydrogen ion concentration. And we could legitimately measure it in terms of powers of 10. So we could measure it from 10 to the 0 through 10 to the minus 7 to 10 to the minus 14. These would be allowable values, with 10 to the minus 7 being the hydrogen ion concentration of pure water. But it becomes tedious writing out concentrations as powers of 10. So instead, they've developed a scale called the pH scale that is based around the hydrogen ion concentration, but it involves taking the negative log of the hydrogen ion concentration. So if we take the negative log of 10 to the minus 7, you get a value of 7. 10 to the minus 14 gives us a value of 14. And as you might guess, 10 to the 0 gives us a value of 0. So the pH scale actually goes from 0 to 7 to 14, 7 being given as neutral, and then 0 being the acidic end and 14 being the basic end. Why that way? because let me erase this. And I think I can bring this back down again, for the time being at least. Why am I getting the highlighter? Because I've got the highlighter pegged. Let me take out this. There we go. So this will be the hydrogen ion concentration. This is the pH value. So this is 10 to the 0, 10 to the minus 7, 10 to the minus 14. An acid is something that adds hydrogen ions. So the increase in hydrogen ions is this way. So this is the acidic end or the acid end. So that should tell you it increases the hydrogen ion concentration. Going this way is the basic end. And this decreases the hydrogen ion concentration. So if you take something like HCl, hydrochloric acid, and dissolve that in water, you get H plus Cl minus. And obviously you are getting an increase in hydrogen ions. So this is acidic. If, however, you get something like sodium hydroxide, NaOH, that gives you sodium ions plus hydroxide ions. And you might ask, well, how does that decrease hydrogen ions? Well, remember, if one goes up, the other goes down. So if you add in hydroxide ions, that goes up, and hydrogen ion concentration therefore must go down. So let me change this. So that's going up. So hydrogen ion concentration must go down as a consequence, because if one goes up, the other goes down. Here we've got a direct increase in the amount of hydrogen ions, so it's very obvious why that's acidic. Here, it's not immediately obvious why this is decreasing the hydrogen ion concentration and therefore should be considered basic. But as soon as we remember that hydroxide ions going up means hydrogen ions going down, then we understand why this is considered to be basic, because it is actually decreasing the hydrogen ion concentration by increasing the hydroxide ion concentration. So this is the basic pH scale. And we have to make sure that we remember to correlate the pH numbers to the actual hydrogen ion concentration. So as the pH numbers go down, the hydrogen ion concentration is actually going up. As the pH number goes up, the hydrogen ion concentration is actually going down. Now, there is another thing that I want you to be aware of, because this will also catch you out as we're thinking in terms of pH, and it's this. If you go from pH so if you go from pH 7 to pH 6, the hydrogen ion concentration is increased by 10. That's a 10-fold increase. If you go from pH 7 to pH 5, the hydrogen ion concentration has increased again, but not by 20, but by 100. Because it's 10 times 10. Remember, it's powers of 10. So the difference between 7 and 6 is 10. The difference between 6 and 5 is 10. But we're not adding them, we're multiplying them. It's powers of 10. So every whole number pH move is an increase or decrease of a power of 10 in hydrogen ion concentration. So if we went from 7 to 4, the difference would be 1,000-fold change. So there are two features of the pH scale that make it a little bit counterintuitive. It's that as the pH numbers go down, the hydrogen ion concentration is actually going up, and as the pH numbers go up, the hydrogen ion concentration is going down. And each change in whole number pH value is a 10-fold change in hydrogen ion concentration. So if we go 2 pH units, it's not a 20-fold change, it's a 100-fold change. If we go 3 pH units, it's a 1,000-fold change. If we go 4 pH units, it's a 10,000-fold change. Very, very important that you have a very clear understanding of these changes in hydrogen ion concentration. Otherwise, it becomes very, very confusing to understand the pH scale. This is one of, in thinking about the pH scale, this is one of the things that gets everyone very, very confused. So make sure that you clarify for yourself these correlations between the actual hydrogen ion concentrations in terms of powers of 10 and the pH values that correlate to those powers of 10 and what the changes in each direction actually mean. That's also really important. So here are some common ingredients that you may be very familiar with or maybe not so familiar with, and they're known pH values. So battery acid, which is sulfuric acid, actually has a pH of around 1, very, very acidic. Will eat through metal, eat through your clothes, eat through your skin, very, very corrosive because of the high acidity. Surprisingly, your stomach is at pH 2 because it secretes hydrochloric acid. And this is one of the misunderstandings that people have. Your stomach is supposed to be acidic because it aids in the digestion of protein. In fact, the enzyme that digests protein in your stomach works best at pH 2. And if it gets, if the pH of the stomach gets raised too much, so you move from pH 2 more towards pH 7, neutral, by the time you get to around pH 4, the breakdown of protein is essentially stopped. And if you don't begin the digestion of protein in your stomach, the ongoing digestion that takes place in the small intestine won't take place either, and you'll get no benefit from the protein, and there will be consequences for that. This is why something like alkaline water that is sold by some companies to neutralize the acid of your stomach is ridiculous. It's totally ridiculous to drink alkaline water because your stomach needs to be acidic. The digestion is not going to take place properly if you neutralize the acid. You would only ever want to temporarily neutralize the acid if, in fact, the little ring of muscle that seals off the top of the stomach from the esophagus allows some of the acid to leak through and you get heartburn. Because the stomach secretes material that protects itself from the acid, and so long as that layer of protection is intact, the acid cannot harm the stomach at all. But the lining of the esophagus has no protection. So if the acid material gets pushed out back up into the esophagus, what is referred to as reverse peristalsis, then the acid will burn the lining of the esophagus and you suffer from heartburn, and you might want to neutralize the acid at that point. Or if you have some ongoing problems with your small intestine, you may want to neutralize the acid a little bit or reduce the amount of acid that's produced. But you would only do that under the guidance of a physician. This is not something where you would self-diagnose and self-medicate, because you can create all sorts of issues for yourself by incorrectly altering the pH of the stomach. It is not something to be played with, because your body systems function at designed specifications. They really do function at very specific, under very specific conditions. And when you start messing with those conditions arbitrarily, you create more issues than you are potentially fixing. It's really important that you understand the significance. And by the way, this is one of those topics, the notion, the idea of pH and its effect on the body. This is one of those topics that we get feedback from the nursing program, from the allied health program, and from the medical school over at UCF, that the faculty members in those schools wish students would have a better understanding of pH. In other words, would remember what they are supposed to have learned about pH in this class. And that is a really, really important thing for you to bear in mind. I have talked to faculty members in our allied health science program, in our nursing program, and also faculty members in the medical school over at UCF, and they've all said the same thing. pH is one of those topics that we really wish students coming into our programs had a better understanding of, that they actually remembered what they would learn in this class, or should have learned in this class. So don't walk away thinking pH is too difficult to understand or it's not important to understand. It's actually incredibly important to understand. I'll give you another reason in a moment. Wine and cola are acidic because of the dissolved carbon dioxide. When carbon dioxide dissolves in water, you get a weak acid called carbonic acid. We'll talk more about carbonic acid a little bit later. Tomato juice is acidic because of the presence of vitamin C, which itself is acidic. Beer is acidic because of the dissolved carbon dioxide. Black coffee is acidic because of the presence of materials called tannic acids, that are known as tannic acids because they were the original source of tanning for leather. And so the tannic acids are what give coffee both its acidic nature and also its blackish brown color. Rainwater is becoming more acidic because of some of the gases that we pump into the atmosphere, particularly carbon dioxide. It should be closer to pH 7 in its purest sense. Urine is pH 6 because of the presence of uric acid. Saliva is around 6.8. Blood is around 7 to 7.2. Pure water, of course, is pH 7. That's the neutral. Seawater is mildly alkaline because of all the dissolved salts, which are themselves mildly alkaline, or a lot of them are. The small intestine runs at pH 8, so obviously coming from the stomach at pH 2 to the small intestine at pH 8. We are going to raise the pH, but we do that naturally. The body does not need assistance through alkaline water. It is perfectly capable of raising the pH to the appropriate level using its own secretions, and does so very well. And you want to let your body do that naturally to promote good digestion. Milk of magnesia, which is often used as an antacid or anti-acid, is actually magnesium hydroxide, so it's adding hydroxide ions. Household ammonia, bleach, contains calcium hydroxide and calcium hypochlorite, both of which are alkaline materials. Household ammonia is also a base because it can actually grab hydrogen ions from solution. Ammonia can actually grab hydrogen ions, so it functions as a base. oven cleaner is either potassium hydroxide or sodium hydroxide. And so both of them add hydroxide ions, so they are very, very alkaline, strongly alkaline. It should never be handled with bare skin because they are equally corrosive, just like battery acid. And in fact, you can tell whether you've got oven cleaner on your hands because it'll feel soapy. It'll have a soapy feel. And if you feel that, that soapy feeling, you really need to wash your hands immediately because it'll start to eat the skin again. Bad news if you get it all over your skin. So one of the things that we do know is that salts are the product of acids and bases. And there's a little saying that you learn in chemistry class. Let's see if I can bring up the pen. Sure we've got that. An acid plus a base gives a salt plus water. So we use the term salt is actually a chemical term. Table salt is a form of a salt. It's a type of salt, but the term salt is a chemical term. Salts are substances that are made out of oppositely charged ions. We learned about this back in chapter 2. So we need to bear that in mind. So how can we see this play out in this equation? Sodium hydroxide plus hydrochloric acid gives sodium chloride plus water. Excuse me. Let me break this out for you. So let's start out with hydrochloric acid. So HCl. If I dissolve that in water, it's going to give me hydrogen ions plus chloride ions. So no problem with that one. If I think in terms of sodium hydroxide, that's going to see me, and we've seen this before, that's going to give me sodium ions plus hydroxide ions. Okay, so how does that give me salt plus water? Well, there's the salt. And what's left, maybe I should do this in a different color. There's the water molecule. So in fact, an acid plus a base gives a salt plus water. And if you think about this for a minute, salty water has a pH of 7 or neutral. So an acid plus a base neutralize each other. So that's why if you have an acid stomach and your doctor says, yes, you do need to take an antacid to neutralize that stomach because it's causing you problems, then you would use an antacid like Tums or something like that, because that contains calcium hydroxide or some other hydroxides, metal hydroxide salts, and the hydroxide will neutralize the acid. But this is, again, not something that you do arbitrarily or self-medicate. That's just a recipe for disaster. It is something that you really need guidance from a health professional. Now, of course, many of you have the intention of becoming health professionals. You will get a lot of education on how to counsel your patients about this, or hopefully you will. Because again, this is not something that you arbitrarily mess with. pH in the body is really, really important, and it's not something that you want to play with. So how do we know that it is very, very important in the body? Because our bodies go to a great deal of trouble to maintain pH within very defined ranges in different locations. So the reason or the way in which the stomach maintains a pH of 2 is to actually secrete hydrochloric acid. The delicate lining of the stomach is protected from that hydrochloric acid so it doesn't get eaten away, but it secretes that hydrochloric acid specifically to maintain that acid environment. The pH of the small intestine is maintained by secretions from the liver and stored in the gallbladder. These secretions, called bile salts, are mixed with the food as it passes out of the stomach into the small intestine to raise the pH from pH 2 to pH 8. And then the body works really hard to maintain the pH of the small intestine at pH 8 to promote good digestion. In the blood, we want to see the pH of the blood maintained at around pH 7 to pH 7.2. If the blood becomes too acidic or becomes too alkaline, organ damage can occur, tissue damage can occur, cell damage can occur. So we don't want the blood to deviate very much from a pH of 7 to 7.2. The problem is that while oxygen is carried on the hemoglobin in the red blood cells, carbon dioxide is primarily carried by simply being dissolved in the blood plasma, which is largely water. Some carbon dioxide can be carried on hemoglobin as well, but the vast majority of carbon dioxide is carried by simply being dissolved in the blood plasma. And so when you dissolve carbon dioxide in water, you get something called H2CO3, which is called carbonic acid. And the reason why is because that, in turn, breaks down to a hydrogen ion plus HCO3 minus, and this is the bicarbonate ion. But the good news here is that the bicarbonate ion functions as a buffer. A buffer is simply a chemical that can react to the change in hydrogen ion concentration to correct it back to where it ought to be. So we want the blood to maintain a pH of around pH 7. If too much carbon dioxide becomes dissolved in the blood so that the hydrogen ion concentration goes up and the blood becomes acidic, then the bicarbonate ion can soak up the extra hydrogens because it has the ability to bind up a hydrogen ion and reduce the number of hydrogen ions in the blood and stop the blood from becoming too acidic. On the other hand, if there are not enough hydrogen ions in the blood and the blood is starting to become alkaline, then the bicarbonate ion has a hydrogen ion to give up, and so it can increase the hydrogen ion concentration and stop the blood from becoming too alkaline. So a buffer, or the job of a buffer, is to simply maintain the pH at a particular level. And bicarbonate ion works really good as a buffer around pH 7. Different substances act as buffer at different pHs. So for instance, in our biology lab, we have a shelf that contains buffers, different buffers that work at different pHs. So we can create a solution with a pH of a particular value by using a buffer that works really good at that pH, and by using that buffer knowing that that solution will stay at that pH because the buffer will keep it there as we do things with that solution, carry out chemical reactions or whatever it is that we're trying to do. And so if we were doing wet labs, if we were actually doing our labs in the lab space, we would be working with buffered solutions, and you would get to see the effect of the buffers and pH on different types of chemical reactions. You will see that in the virtual labs later in the semester when we do the enzyme lab. You'll see the effect of pH on chemical reactions there, because enzymes and their chemical reactions are really, really sensitive to pH, hydrogen ion concentration. So buffers are really important chemicals to know about as well. And you're going to learn about a number of buffering systems that the body possesses, particularly those of you who are going into our nursing program or allied health science program. When you go take your AMP classes here at Valencia, you'll learn a whole lot more about the buffering systems in the body and the value of being able to maintain constant pHs, because the body works extremely hard to make or to maintain constant chemical conditions, an idea known as homeostasis. And the use of buffers to maintain constant pH is part of that homeostasis mechanism. And the fact that the buffer in the blood, the bicarbonate ion, is a simple product of how the carbon dioxide is transported in the blood is an example of how organisms, and all organisms that transport carbon dioxide the way we do, which is basically all terrestrial tetrapods and fish and any organism that has blood and hemoglobin, is simply, these organisms are simply taking advantage of the fact that dissolving the carbon dioxide in water produces a buffer, bicarbonate ion, that is really, really good at maintaining pH at pH 7, which is exactly where you want the blood to be. And so rather than having to come up with some fancy system to maintain the pH of the blood at 7, you simply take advantage of the presence of the bicarbonate ion, something that occurs naturally because of the dissolving of the carbon dioxide in the blood plasma. So that's buffers. So this diagram just simply gives you, again, the range of the pH scale, and also what happens both at the neutral point in terms of hydrogen ion concentration and hydroxide ion concentration, and then what happens at the acidic and basic ends. It's just a nice summary. So one of the issues that we need to pay attention to is the fact that with all of the carbon dioxide that we pump into the air, and remember, carbon dioxide, when it dissolves in water, creates carbonic acid. Not only does that happen in the bloodstream, but that also happens to the carbon dioxide that is pumped into the atmosphere, because there's water there as well, and the carbon dioxide dissolves in the water. This is the reason why rain has always been mildly acidic, and it does that mildly acidic rain does things like dissolve limestone and create caves. It creates the cavities in the limestone that forms Florida, and that's where our fresh water is found, in the big underground cavities that have been formed by the very mildly acidic rainwater that's eaten through into the limestone and created these cavities. When that limestone gets too thin, we have a cave in and you get a sinkhole. Or if the water is removed from the cavity, the limestone may not be able to support itself and it collapses in and you get a sinkhole. Either way, it's because the limestone has been eaten away by the mildly acidic water, either the rainwater or the underground water that's flowing through the limestone. But when that acidity turns up in the ocean, that creates a problem for things like corals and other organisms that need to extract calcium and carbon dioxide out of the water to create the little skeletons as calcium carbonate. So here's calcium carbonate. This is the material that forms the skeletons for corals. It forms the hard part of shells for seashells. Anything that has a calcium carbonate based hard parts, even bones in fish, are built from the calcium carbonate. As you acidify the ocean, it becomes increasingly difficult to extract the calcium carbonate out of the water. And this is affecting the corals, it's affecting the mollusks, the snails and so forth that live in the oceans. They're finding it increasingly difficult to get calcium carbonate out of the water to build their skeletons. And it's creating die-offs of the skeleton, of the corals. It's one of the reasons why reefs are in trouble. There are a number of different reasons why reefs are in trouble. This is just one of them. And it's also creating problems on dry land as well. One of the places that I really have enjoyed visiting over time has been the Great Smoky Mountains up in North Carolina. And when I first went up there about 20 years ago or thereabouts, and went to the highest point, the lookout on the highest point, you could see green trees for as far as you could see. If you go up there now, you're going to see a lot of dead trees. And the reason why is because of all the polluting gases that have been pumped into the atmosphere out in the Midwest that have dissolved into the water and been carried eastwards. And when they get to the Great Smoky Mountains as the first mountain range that the air reaches, it goes up, it cools down and it starts to rain, and the rain comes out in a more acidic form because of all the dissolved gases. And plants don't do well when the soil gets acidified, particularly if they're used to a more neutral soil. And so as the rain becomes more acidic, it actually has started to kill off the forests. And now when you look out over the forest from the lookout at the top of the Great Smoky Mountains, you see a lot more dead trees. A lot more than I have ever seen in the 20 odd years that I've been going up there. It's not pretty to see. And if you go to Europe, one of the famous forests in Europe is the Black Forest in Germany. It pretty much doesn't exist anymore because of the industrial pollution that's acidified the soil through the rainfall. And this is an increasingly serious problem as the rain becomes more and more acidic because of the atmospheric gases that are present. It's having consequences for the growth of plants. As the soil becomes more acidic. They don't typically favor acidic soils. So this is something that we are doing. We are directly responsible for these gases appearing in the atmosphere, and we are directly responsible for this acidification and the loss of these life forms. And there's no way that we can escape from this responsibility, because it is quite clear that this is what we are doing. So our final concept check for the morning, and this shouldn't be a terribly difficult thing to do. So we've talked about these. Let me stop for a minute while you read these questions through. I'll read them out and then I'll stop for a minute. So a solution of pH 9 has how many times the concentration of hydrogen ions compared to a solution at pH 4. And if a solution has a hydroxide ion concentration of 10 to the minus 11, what is the hydrogen ion concentration and the pH of the solution? So let's take a look at these questions so we can finish up. So a solution of pH 9 has more or less hydrogen ions. Well, the truth is it has less hydrogen ions, because remember, as the pH number goes up, the hydrogen ion concentration goes down. So it's actually going to have less hydrogen ions. But the question is, what difference in hydrogen ion concentration is it going to be? Well, it's 5 whole number pH units. And that means it's 10 times 10 times 10 times 10 times 10. That's 5. So it's going to be 10 to the 5-fold difference. And 10 to the power 5 is 1 with 5 zeros after it. So that would be a 100,000 times difference. So 10 to the 5 times difference. And the difference is less, 10 to the 5 less concentration. So if we're looking at the next one, if a solution has a hydroxide ion concentration of 10 to the minus 11, what is the concentration of hydrogen ions and the pH of that solution? So the first thing we need to remember is that the concentration of hydroxide ions multiplied by the concentration of hydrogen ions must always equal 10 to the minus 14. So we know that OH minus equals 10 to the minus 11. So if we forget the negative number for a minute, and we just think 14 and 11, the difference between 14 and 11 is 3. So that tells us that the hydrogen ion concentration must be 10 to the negative 3. So negative 3 plus negative 11 gives us 10 to the minus 14. So the hydrogen ion concentration is 10 to the minus 14. Actually, what I'll do, I'll bring this over here. So the hydrogen ion concentration equals 10 to the minus 3. And we know that the pH is the negative log of 10 to the minus 3, but we know that to figure out the pH, we simply take the positive whole number, power 10, so the pH is 3. So hopefully that's reasonably transparent to you. That's easy for you to understand how to do that. These are the sorts of things that you might be asked to do in an exam question. There's a hint. So that brings us to the end of this presentation. Again, as always, if you have any questions, concerns, or comments about anything that I've covered in this presentation, feel free to contact me by email or come see me during office hours, and let's talk about what is confusing you or what you need some clarification on. I'd be more than happy to help you out. But if all else fails, or if you feel uncomfortable about doing that, and hopefully you don't feel uncomfortable doing that, by all means go and take a look at the study area in Mastering Biology. Make sure that you take a good look at the dynamic study module for this chapter, because there are questions in there that cover all aspects of the properties of water, in particular, and with some questions about molar calculations and pH calculations to help you practice that. And I will make sure that I send out the worksheets that cover all of these as well. So that's water. The next presentation, which I will be recording within the next day or two, will cover the carbon side of life, the large organic molecules that make up the rest of organisms that are not water, about 30% of the average organism. So I'll see you then when we start that presentation. So bye for now.